I decided to do a little video on different transmission lines that are used, transmission lines that are used in your microwave technologies, in microwave engineering. So there are different transmission lines that are used in microwave engineering. One of the most common is the microstrip line, where you have a insulator substrate upon which you have copper lines, and at the bottom of which you have a ground reference plane. This is a two conductor transmission line, where basically you have this is one conductor and this is another conductor. So basically you have two conductors in this transmission line. This is called microstrip. This actually stems from an older transmission line, which is a coaxial transmission line, which is another two conductor transmission line. In coaxial, we have a center conductor, and above we have a shielding conductor, metal shielding conductor. So these are both are conductors, conductor 2 and conductor 1, and in between this space is filled with some kind of insulator. It can be air also, but it is filled with some kind of insulator. In many cases it is Teflon. So coaxial transmission lines were one of the first transmission lines, and you can see there is an evolution from coaxial transmission line to microstrip. So maybe if you take the cross section of the coaxial transmission line, it can be converted to something like this, and this is basically a strip line. Some people call it embedded strip line also. So you can convert the outer circular shield to a square or rectangular shield. There is still insulator inside. This is insulator, and we can also convert the internal conductor to a square or rectangular thing. So this is strip line. Some people also call it embedded strip line because it is embedded. The internal conductor is embedded inside the insulator. So this is the embedded strip line. Then we can have a strip line which is suspended strip line, but let us not talk about that first. Then if we remove the top insulation and only think the insulation is at the bottom side, the top side is filled with air, then we can get a kind of a air and this insulator, and in between we have a strip line. Next, it was found that if this distance is h, this is the substrate thickness is small enough, then all the electric fields or the energy fields will be mostly contained within this substrate. Thus, we can do away with this shielding structure. So that will lead to our microstrip kind of structure, where we have this center conductor, yes, but now it is not a center conductor, and we have a metal at the bottom conductor, and we have the insulator. So it's a simple way of how we went from coaxial to the microstrip line. Now if you look at the microstrip line conductor microstrip lines, this if you look at the microstrip lines cross section, then we can think about the electric fields that is operating in between them, and also the magnetic fields that is operating in between them. To start that, let us start with the cross section of coaxial lines. So in coaxial line we have a center conductor and we have an outer conductor, and in between we have some insulator. So obviously if there is a current flowing, there is some kind of in between the inner conductor and outer conductor, if we put some kind of signal, so at a point of time and at a particular cross section, we shall have either a plus, that is say positive direction, there is some current flow in the shield, and obviously there will be a return path for the current flow, and that is through the shield. So if we take this positive and this as negative, so electric fields will direction of electric fields will be like this, right? So there is and your magnetic field direction will be like this. Now if we the direction will be this. Now if we consider similarly, if you consider the electric field in microstrip line, the electric fields will be like this, but at the outer section, if the h or height of the substrate sustains, then some of the electric fields will come out of the substrate, and then it will include a little bit of air also. It will have some of the electric fields will go through the air also, and these are called fringing fields. These are called fringing fields. So now one question might come, why how much of the electric field will be inside the substrate, and how much of how much of it will go to air and come like this. So that will depend on the epsilon r, or dielectric constant, or permittivity of the substrate or insulator, or the dielectric. Now why? Because dielectric constant determines how much of the electric field it can store inside the dielectric. Okay, so it's a measure. Mostly it is defined as epsilon r, which is a relative dielectric constant, and it's a measure of how with respect to air, how or vacuum, how much more electric fields a particular dielectric can contain. So if your epsilon r is very high, it may so happen your fringing fields are very less, because most of the electric fields are then contained inside this one. Now we talk about a particular term called mode in transmission lines. So mode is basically the field, a representation of how the fields are oriented inside the transmission line while it is propagating inside the signal. So in this particular case, in this coaxial case, the electric field is coming out of the page, right? They are coming out of the page, and your the propagation of the signal is coming out of the page. That is the direction, and let us draw it here. So this is the direction of propagation of the signal, and your electric fields are all perpendicular or orthogonal to that direction, and your magnetic fields are also perpendicular orthogonal to that direction. So this particular orientation of electric field with respect to the propagation direction of the actual signal is named as transverse, or transverse means your perpendicular orthogonal transverse electromagnetic or in short this is called TEM mode. In case of this in case of microstrip lines also, the magnetic fields are obviously they are like this. If the signal is coming out of the page again, then the magnetic fields are like this. So here also mostly the electric fields and magnetic fields are perpendicular orthogonal to direction of propagation. So this is almost TEM. It is not particular TEM. Maybe on some other occasion we shall talk about why it is not completely TEM. But so this is called TEM, but it is quasi TEM or almost TEM. It almost behaves like the TEM wave. Now let us talk about the distributed nature. Now let us talk about the distributed nature of the transmission line in microwave. So we have earlier talked about read about network analysis and circuit theory, in which we dealt with lumped nature of circuit elements and all. And that stems from the idea that if there is a resistor or capacitor or inductor in your circuit, we are mostly dealing with low frequencies where your wavelength is much higher than your circuit elements, because mostly you can relate to this formula where your frequency and wavelength multiplied is equals to velocity of light. So if your frequency goes low, it means your lambda or wavelength of the signal goes high. So what we are talking about? We are talking about this. So we are talking about wavelength. Frequency is the repetition. Wavelength is for one full cycle of your signal how much it propagates. But in case of low frequencies, and if you connect a circuit, if you connect a sinusoid, low frequency sinusoid to a particular, say, resistor, at a particular point of time, your wavelength is such that this resistor is much in size is much lower than your wavelength. Thus, your the voltage across the resistor does not change that much, because the size is minuscule towards the wavelength. But at higher frequencies, when your wavelengths get comparable to your resistor size or your lumped element sizes or your network element sizes, what happens? There is a considerable potential the change across distribution, but there is a considerable potential change across the resistor. So you have a different potential distribution across your resistor. So at some point it is, say, 0 volt. At some point it is reaching a maximum. At some point again it is crossing a 0 volt, and at some point it is again reaching a minimum. So across the resistor itself there is a potential distribution, because your wavelength is now comparable to your element, and this will happen if you are using a capacitor or an inductor at these frequencies. It may so happen even at higher frequencies. It may so happen your these lumped elements, resistors, capacitor, inductors are such in size that it can have multiple wavelengths. It is comparable to multiple wavelengths in size. Like say if you have a 1 gigahertz, just for an example, if you have a 1 gigahertz signal, so your wavelength is around 300 millimeter, and that is about 3 centimeter. Say any resistor that you are using, if you are using a SMD surface mount device, a cheap resistor, say of 0603 imperial size, then your this dimension is mostly 6 mil. This is around 6 mil, 60 mil, sorry, 60 mils, which around is 1.6 mm. So at 1 gigahertz, this 0603 SMD component is much smaller than your wavelength. But say we go to now 10 gigahertz, and now your this wavelength becomes about 30 millimeter. So there is almost some comparability. Now let us go for even say higher frequency, say at 100 gigahertz or something, where your wavelength becomes 3 millimeter or something. So we are getting more comparable to your SMD component. So there will be again a distributed nature of the signal over the component. So whenever we are talking about high frequencies, any lumped component or anything, there is a distributed nature of that lumped component. Similarly, when we are talking about say microstrip line or a coaxial line as such, there is also a distributed nature of we can model these coaxial line or this microstrip line using a distributed model, where we assume that the transmission line comprises of distributed resistors, inductance, capacitance, and conductance. Where this comes from? The resistance comes from the conductors, because inherently there will be a resistance in the conductors. They are like if we are using copper or aluminum, anything. The G or conductance comes from the insulator that we use or dielectric that we use, and the inductance comes from again this conductor, and the capacitance comes from this one. The capacitance is in between the two conductors. If I take a infinitesimally small length delta Z, then we can model this using lumped equivalents of this RLCG, and which is all these units are per unit length or something, into and that will give us our transmission line model. So how they are converged? So along the length of the say this conductor, we have resistance and we have inductance, and along through this insulator we have the capacitance and we have conductance. In case of in case we use ideal conductors, then R becomes 0, and also this G, if we use ideal insulators, this G becomes infinity. Then it only becomes an LC circuit. And you can think that the transmission line is comprises of this continued repetition of this unit RLCG. And this repeats. Now, if we ignore, not ignore, if we take the case of ideal conductor and dielectric, then we have your resistance equals 0, your resistance per unit length equals 0, and your conductance per unit length is also equals infinity, because we have a, if you have a perfect insulator. Then this circuit becomes a normal LC circuit, which is a low pass kind of structure. So here we get the idea that inherently your two conductor transmission line is a low pass kind of structure. But from this model you can see one curious thing, that we can model any two conductor transmission line by changing its parameters. We can model it to some kind of inductor or capacitor also. Let us take the example of microstrip line. So this is the top conductor, this is the substrate, and again we have a ground. Now if we on the top side, if we just change the width of the transmission line so much that its inductance becomes very small but its capacitance becomes very high, then it almost represents a shunt capacitance with the transmission line. So by making the top conductor width high, we can make it behave like a capacitor in shunt. Similarly, by making the top conductor width much smaller and giving it some running it for some length, we can model it as an inductor. But this is a series inductor. This is a series inductor. So here the width we have decreased the width. Here we have increased the width. So this is a capacitor. To just understand, so basically we have increased the microstrip top conductor and bottom there is a ground. So obviously from your capacitor epsilon A by D, we have increased the A dimension in between the top conductor and the bottom conductor. So it gives rise to your capacitance value. Along with that, it will also decrease your inductance. And here we have increased the inductance value, and so and obviously your now your capacitance is very small, so it can be ignored. Then it gives you a series inductance. Thus, we can utilize our distributed parameters from our distributed model. We can utilize this nature to create a shunt capacitor and a shunt inductor. Let us now revert back to our lumped component discussion for some seconds now. So if we have a capacitor or an inductor or a resistor, while they are utilized in lower frequencies, then they behave like a simple capacitor and simple inductor or simple resistor. But now in high frequency, where your again wavelength is comparable to the actual physical dimension of your live component, what happens, the associated circuitry in physical circuitry of a capacitor or inductor or resistor, they play a bigger role. So a lumped capacitors, again an SMD lumped capacitor, when it will be placed on a circuit, there will be some soldering involved, and there obviously will be some kind of metallization at the both ends of the capacitor. This will lead to an inductor, and your if we think about it, your capacity, there will be also some kind of resistance in between, and also in these two pairs there will be a capacitance also, and then you have the actual capacitance here, and maybe some there because of the resistance of the conductor that is used, there will be some kind of resistance also. So we have this kind of package inductances, package capacitances, and some kind of stray resistances along with our capacitance. This does not play much a role at lower frequencies, but at high frequency they play a big role, because your capacitance represents as a reactance which is of the form of 1 by omega c, and your inductance gives a reactance which is of the form of omega L. So you can see the nature, by nature they are, if they are in series, so by nature they are, with increase of frequency, with increasing frequency, one reactance goes down and the other reactance goes up. So if you are dealing with, say, a capacitor, and you are increasing the frequency, and you are looking at the impedance, that is your resistance plus reactance, then what will happen, if you are dealing with a capacitor at the lower frequencies, your capacitive nature will be the most significant. So as frequency increases, your capacitance goes down, but obviously there will be a frequency at which your omega L and omega C, they will cancel each other out, because if we represent it as this, minus j by omega c, so they will cancel each other out at a certain frequency for whatever c value and whatever stray inductance values you have. They will cancel each other out. That is the resonance frequency. This is the resonance frequency of that particular SMD component, of that particular any lumped component. So it is called the self-resonating frequency, SRF. And after that your inductance value will go up, and then you have this kind of nature. So you can only use that lumped component up to a certain SRF value that is defined by its physical structure, and above that it will start behaving like a inductor. Similarly, if we have an inductor in, say, again an SMD kind of package, then again it will have some kind of package capacitances, the capacitances that are in between this end and this end, and some resistances, because again anyway inductance is created by some convoluted metal conductor, thin metal conductor. So there will be some kind of resistance structure also, and again there will be some package inductances. So here also we shall see a nature where you are with the frequency, your lumped components will first show as if it is working as a inductor only. Inductive impedance will go up, and then after some certain SRF, depending on the physical structure of the component, it will go down, because the capacitive nature will take over. So here we can see mostly that we can use with certainty a component until its SRF. After that we need to be cautious about what kind of impedance we are getting from that particular lump component, so that whether that meets our requirements of how we need that component to work at that particular frequency. So it is from this you can again we can see, so it is very difficult to use a lumped component at high frequencies. So there will be, because when we are talking, most of the SMD components which are nominal 0603 imperial size, that is 60 mils into 30 mils kind of size, or say 0402 imperial size, that is 40 mils into 20 mils, they stop working in between 1 gigahertz to 10 gigahertz. So above that, most of the even that is also for particularly made for RF kind of components. Yeah, a normal, say if you are talking about a simple thick film resistor, that will stop working at even that might stop working even at 2 gigahertz or 3 gigahertz, because some kind of inductance or capacitance will take the capacitive reactance will take over from its the pure resistive form. So it is almost impossible to use, not impossible, but it's very difficult to use unlumped component at this high frequency. So we need to have some kind of distributed component by utilizing the distributed parameters of the transmission line itself. So there, this kind of the shunt capacitance and inductances made from modified transmission lines come in handy. To complete this discussion, we shall also talk about one more thing, which stems from transmission line impedance equation. We shall not derive the equation here. So we shall use the transmission line impedance equation, which is form is this. So where we can define an input impedance of a transmission line of length L with a load impedance of ZL at the end, and the characteristic impedance of the line as Z0, using this equation, where Zin equals to Z0 into ZL plus JZ0 tan beta L upon Z0 plus JZL tan beta L. Where to show it pictorially, so a two conductor transmission line is here, and we want to see its input impedance Zin, and there is a load impedance ZL connected at the end of this transmission line of length L, and your propagation constant is beta. Beta is nothing but 2 pi by lambda, and we have a characteristic impedance Z0 for this particular line. What is characteristic impedance of transmission line? Maybe we can discuss on some other time. Then this gives you the equation at input impedance. Now what is curious about it is that we can utilize these two parameters. Say for a particular Z0, we can utilize these two parameters, ZL value and the length L, to represent any impedance, be it a capacitive impedance, capacitive reactance, or the inductive reactance at the Zin. So by utilizing this kind of structure, we can create a capacitor or inductor in any circuit. Let us talk about it further. Let's consider first one case where ZL equals to infinity, that is open circuit. So at the end of the transmission line, we have an open circuit. And another thing is, let us consider. So in this case, let us take ZL equals to infinity, that is an open circuit, and let us consider the case where L equals to lambda by 4. That will mean your beta L terms become pi by 2, or tan beta L equals to tan by 2, which is equals to infinity. So now if we take a special case of if our length L is equal to lambda by 8, then beta L is represented as pi by 4 and tan beta L becomes 1. So our previous equation, here we replace tan beta L is 1, and we get Zin equals to Z0 into ZL plus JZ0 by Z0 plus JZL. Now here, if we replace our load impedance first with short circuit, then we see that our input impedance becomes JZ0, which is nothing but an inductance. so it becomes inductive. And if we replace our ZL as open circuit, then we get Zin as minus Z0, JZ0, which is nothing but capacitive. So thus, as utilizing a particular length of this transmission line and utilizing open circuit or short circuit at the end of the transmission line, we can represent an inductor or capacitor as the input impedance. What does this signify? Say this is our normal microstrip transmission line. This is the top view. The bottom is there is a ground. Now if we have this kind of structure, open circuited struct transmission, that is your lambda by 8 length, then this will represent as a capacitor at this point. So our equivalent circuit becomes this. Similarly, in the transmission line, the microstrip line again, if we have a stub, but at the end we have a short circuit utilizing a via ground. Ground is stub to the bottom ground plane. There is a ground at the bottom, right? Then this will be seen here as an inductor. So the representation will be like this kind of inductor, shunt inductor. So here we can both make a shunt capacitor and shunt inductor. So earlier we have seen that we are able to make shunt capacitors and shunt inductors. Now we have another way of making a shunt capacitor, which is if we maybe some other time we can discuss, are almost similar ways. And now we also have a shunt inductor. So now we have shunt capacitors, shunt inductors and series inductors. Only thing that is left for again completion of the discussion is the series capacitor. Now for series capacitor, it can be made again very easily. We can have a gap coupled capacitor, just gives an idea. We shall again discuss this with the help of microstrip line. So in the microstrip line, if we just introduce a gap in between the microstrip lines, then this gap will work as a capacitor. If you look at the equivalent circuit of this one, it will look like this. So there will be a capacitance in between the microstrip edges, these edges, and also there will be some capacitance in between this to this, and this is, so we have a gap capacitance Cg here. We can use other different ways of having capacitance. So if you need to increase the gap capacitance, we can again increase this edge section to make the gap capacitance work, increase the gap capacitance. Or we can also introduce some kind of interdigited combing kind of structures again to increase this kind of gap capacitance. Again, there are many other ways to increase this capacitance. This is another way of increasing the capacitance. So now we have everything, right? Series capacitance, shunt inductance, series inductance, and shunt series capacitance, series inductance, shunt inductance, shunt capacitance. So I try to give you a glimpse of how we can generate different capacitors and inductors, distributed capacitors and inductors in your with the aid of microstrip lines. But this can be done with other two conductors lines also in a similar fashion. We also discussed how we can derive these values. Hope this helps.